This is 11.3, part D. Limits at infinity. After today, we only have one lesson left to learn for the whole year. I know, crazy, huh? Okay, you've taken limits at infinity before. You have. We've graphed them. We did, yeah, way back in like chapter 1 or 2 or something. And as x goes out to plus or minus infinity, you were trying to find the limit, and we talked about this. And what happened is, usually, we did this with those rational functions that look like this. Let's say there's an asymptote here, and there's an asymptote here. Do you remember these graphs?
Yeah.
And they go like that, and they go like that, and you graph them by hand. You did a really nice job, okay? Well, we're going to try to find the limit as x goes out to infinity. And as x goes out to infinity, this is getting closer and closer to the asymptote. Remember that? Yeah. So like if the asymptote is y equals 1, then the limit as x goes to plus or minus infinity on this graph, the limit would be 1. Because that's what y is getting closer and closer to. Remember, being a limit doesn't mean you equal that value. It means you're approaching it. All right, so knowing that, we need to know what the asymptote rules are one more time. Do you remember your asymptote rules? Yeah? Maybe? Okay, so here we go. Asymptotes. Let's start with horizontal asymptotes. We have two kinds of asymptotes, so we'll do horizontal first. Horizontal asymptotes, and these are all for our rational functions. Not everything we're going to do is a rational function. All the other stuff that we do, you can graph on your calculator and find the limit. I'll show you those too. But horizontal, so this is for f of x equals p of x over q of x, where p of x and q of x are polynomials, and so it makes a rational function. Okay? All right, so here they are. Here are your three cases. Case number 1. It's all about their degrees, okay? Their degrees are the biggest exponent. So if you have a cubic, it has a degree 3. So if their degrees, degree of p of x equals the degree of q of x, okay, then the asymptote is y equals leading coefficient over leading coefficient. Does that ring any sort of bell? A little bit? Maybe not? Yeah? Good. And then let me give you an example of that. Okay? So, and we're finding the horizontal asymptotes because that's what the limit is going to be as you go to infinity. So if you take, for example, the limit as x goes to infinity for 3x squared plus 5 over 4x squared plus 6x minus 1. Okay? That looks pretty tricky, right? It's like, whoa, what's going on here? Yeah. Well, their degrees are equal to each other. So you really kind of ignore all the other stuff. The other stuff is not really affecting this at infinity. As you're going towards infinity, that 5 means nothing. My son asked me the other day, Mom, what's infinity plus 7? I'm all, infinity. You know, it's like, what's infinity plus 5? Still infinity. You're like out there. 5 doesn't matter. So you're really just looking at this right here. And so it's the leading coefficient over leading coefficient. So the limit is 3 over 4. Perfect. You're done. Nice, huh? Aren't those nice? If you remember your asymptotes for those, it's not going to be a problem for you. Okay, number 2. What if the degree of p of x is less than the degree of q of x? Okay. So p of x is smaller and q of x is bigger, then your asymptote is y equals 0. That's your asymptote. And so an example of that would be the limit, and this is for x goes to infinity or negative infinity. So the limit as x goes to infinity for negative 7x plus 1 over x squared minus 5. So the degree of the numerator is less than the degree of the denominator. And it's kind of like this. Like if you were to plug infinity in, right, you have a huge infinity squared on the bottom. So that, like a big number in the denominator and the little tiny number on top, you're going to 0. Okay, so that's a limit. Limit is the horizontal asymptote. All right, and then finally, the third case would be something like the degree of p of x is now greater than the degree of q of x. Oopsie. Sorry. Q of x. Okay, and then for this, there was no horizontal asymptote. Okay, no horizontal asymptote. So these went off to infinity or negative infinity, depending. And so the book, I'm not sure what next year calculus they'll say, but this book says that the limit does not exist. Bless you. Some books will say the limit is infinity or negative infinity, so just to be aware of that. But this book says if you take the limit as x goes to infinity of something like 3x to the 4th plus x over negative 7x squared plus 1, for example. Okay. This right here would be the limit does not exist. Because you're getting infinity over negative, like infinity to the 4th. It's kind of like almost like you just look at these two things and you go 3x to the 4th over negative 7x squared, and then like you reduce them. So you really get negative 3/7 x squared. And so as you're going to infinity, this is actually going to negative infinity. But D&E is fine with me. Okay, that's what the book does. We'll go with that. All right, so those are your horizontal asymptotes. I hope you remember those, and you're going to do those rational ones just like that. So let's do some examples now. So let's do some trickier ones. Number 1, we're going to find the limit as x goes to infinity for negative x squared plus 8 over x minus 2 squared. Okay. Now, some people will look at that and they'll think, oh, I got to FOIL all that out and distribute the minus. Nah, you don't need to do any of that. Okay? You can tell, because you're good at math, you can tell that this is going to be x squared, and your leading coefficient, if you were to FOIL that whole thing out, will be x squared also, or your leading term. And so you get negative 1 over positive 1. Degrees are equal, so the limit is negative 1. Number 2. How about this one? The limit as x goes to infinity of 3x over 5x plus 1. So 3x over, that's an infinity symbol, that's weird, over 5x plus 1 minus 2. Ooh. All right, so we're going to use our properties. Do you remember those properties before?
Yeah, the limit of that would be the limit of that.
Yes, yes. It's almost like distributing the limit to both functions in here. So we take the limit as x goes to infinity for the first one, and what's that going to be? 3 over 5. And then we take the limit of 2 as x goes to infinity. What's that going to be? 2. Remember, it's just a constant. And so we get 3/5 minus 2, which is, what is that, negative 7/5? Gross. Yeah, negative 10/5. Okay. All right. Oh, then they're going to try and really mess with you here. They might throw one of these in. By they, I mean me. And they go like this. The limit as x goes to 0 for 3x plus 1 over 16x plus 2. Something like that. Okay? Now, look where we're going. The answer is not 3 over 16, is it? We're not going to infinity. We're going to 0. You're going to 0, plug 0 in. Right? So the limit would be 1/2. But people are so used to seeing these rational functions, they just think it's, oh, okay, it's leading coefficient over leading coefficient. But that would be if I was going to infinity, but I'm not. I'm going to 0. Okay? So that would be 1/2. All right, so you will also talk about vertical asymptotes. So let's get to that. This is pretty short. We're almost done. It's nice to know when you're almost done, huh? I was doing a workout video yesterday. I'm like, how long is this? She's like, we're almost there. Like right after I said that. It was good. Yeah, I hurt today. All right, vertical asymptotes. Now, vertical asymptotes, if you remember, are the zeros of the denominator. Zeros of the denominator, as long as they are not holes in the graph. Remember the holes in the graph thing? We'll talk about that. As long as they are not holes. Okay? Zeros of the denominator. So let's take a look. For example, if you had something like y equals 5x over x minus 4. Okay? And I asked you, you can find the horizontal asymptote. We just talked about that, right? You can find it pretty easily. So the vertical asymptote would be x equals 4. Vertical line through 4. All right, but what happens is sometimes it looks like a vertical asymptote, but it's not. So if I had this same type of problem, but up top it was x squared minus 16, and in the bottom it's x minus 4 again, x equals 4 is not a vertical asymptote. Yes, it is a hole in the graph. Because once you take this and you factor, you can go ahead and reduce. And what this graph is just simply a line with a hole in it at 4. Okay? So let's talk about the limit of each of these things. So let's go ahead and get your calculator out, because I'm going to let you have your calculator for these. When you get to calculus, AP Calc next year, you might not be able to have your calculator for some of this. But I let my calculus class have their calculator for these things. Okay, so number 4, let's go ahead and we'll take both of these. And we will do y equals 5x, let's call it f of x equals, f of x equals 5x over x minus 4. And we are going to take the limit as x goes to 4 from the right of f of x. We're going to take the limit as x goes to 4 from the left. And we'll find the limit as x goes to 4. Okay? And I'm not going to make you graph these by hand. We did that at the beginning of the school year. You really don't need to now. All right, so take 5x and divide it by parentheses x minus 4. You won't need to draw a graph of it. I'm going to, just so that we can talk about it. Did yours show up? What's going on here? Huh? What? Oh, there it goes. I don't know. My calculator froze on me. It was weird. All right, so we know the graph of this. There is a vertical asymptote at x equals 4. And there's a horizontal asymptote at y equals 5. We don't really care about that, but we'll draw it in anyways. And so this graph, you can kind of see the little corner of it, but it goes like that and like that. Okay. So let's talk about all their limits. So let's do the first one. First one is the limit as x goes to 4 from the right-hand side. So here you are. You're going to jump on the right-hand side of 4. So 4 is right here. Remember, this is the right. This is the left. And we're jumping on and we're going, as we walk towards 4, where's our y value going to? Infinity. It's going to infinity. The y is going up forever and ever as we get closer and closer to 4 from the right. What about the other way? Where's that going? Negative infinity. Perfect. So on the left-hand side, and it's not always that way. Like you think, okay, always on the left it's going to go negative. These could get flip-flopped. And then what's the limit as x goes to 4? Are they going in the same spot? No. So the limit does not exist. Now, that's all well and good, and that's great, and you're allowed to graph that and whatever. But we also have done, you know, the other one. F of x equals x squared minus 16 over x minus 4. And I could ask you here, what's the limit as x goes to 4 plus, minus, and regular 4? So let's talk about that. Limit as x goes to 4 from the left. It's really good, especially if you can't have your calculator, to have a sense of what these things look like. Because if you visually see it in your mind, it's actually easier to do it. So if you were to graph that, you know, that would be fine. But like I said, we've done this one algebraically before, right? If you were to do and go ahead and factor it and simplify this, okay? Then if you plug in 4 from the right, the answer is going to be 8. If you plug in 4 from the left, the answer is still 8. So if you think about this, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, there's a hole in the graph right there. And then it just looks like that. Looks like a line. Like if you were to graph it on your calculator, that would be a line. You wouldn't see that hole there, but if you did go to 4, you'd be like, oh shoot, there's no y value. So from this side, from the right, it's 8. From the left, it's also 8. And so the limit is 8. Yeah. All right, let's do one more. No, I think we're pretty good. If you you're allowed to graph these, okay?